Thanks a lot. Yeah, so in the last few lectures, we've gone through basic aspects of worldsheet string theory at a breakneck pace. So hopefully, some of you that have already seen the material got a little bit of a refresher. And those of you that hadn't seen the material before, hopefully at least have a sense for where some of these kind of string theory results come from. And hopefully after this, it seems a little bit less like black magic if you haven't seen all of these things before. So last time we were studying some fairly simple supersymmetry preserving compactifications to Minkowski space times a manifold of special holonomy. And in particular, we spent most of our time on the case of toroidal compactifications. Tori have trivial holonomy. They preserve all the underlying supersymmetry of the parent theory. And there's so much control from all of the supersymmetry that's preserved that we can say a lot of things about them and their dualities. In fact, we even have a global form for the moduli space. And we wrote down some of these double coset type moduli spaces for various compactifications, where they're in particular quotiented out by some interesting groups of T-dualities. And sometimes also we found that the dilaton gets implicated and mixes with the metric and the B field and the Wilson line and perhaps the Ramon-Ramon degrees of freedom into some larger group that's often called a U-duality group because it combines T-dualities with S-dualities that can act on the dilaton or the axiodilaton. That's kind of the nice thing about a lot of these string compactifications, or string dualities rather, where, in a field theory, you're not only mapping field variables from one side to the other in some really complicated way, you also have to map parameters like the coupling constant. Here in string theory, of course, there are no free dimensionless parameters. They're set by the vevs of these moduli, and the moduli can all mix up together in interesting ways, and we can study these maps quite explicitly. At least in certain cases. Good, so for today, I wanna talk mostly about mirror symmetry and compactification on Calabi-Yaos. And I will very, very quickly, very soon retreat to the worldsheet because I want to use mirror symmetry kind of as a prototypical example to introduce some very general things, general techniques and perspectives that arise in the mathematical physics, mathematical string theory community these days more broadly. And we saw actually very happily in the last lecture a little bit about type 2 compactifications on Calabi-Yau manifolds, which certainly makes my job a little bit easier today. So today, mirror symmetry from the worldsheet. But we've seen that if we compactify either type 2a or type 2b on some compact Calabi-Yau threefold, you saw in your last lecture that you obtain an n equals 2 supergravity theory in 4 dimensions. And the supergravity theory is going to contain a supergravity multiplet, and additionally, it's going to have some hypermultiplets and some vector multiplets. And in particular, if you compactify type 2a on a threefold, the number of vector multiplets is going to be given by the Hodge number H11, and the number of hypers is going to be given by H21 plus 1, and vice versa in 2b. Namely, the number of vector multiplets is H21, and hypers H11 plus 1. So like I said, I'm going to retreat to the worldsheet, but if I wanted to imagine things as happening in the effective supergravity theory, and I wanted to just think of things at the level of a Kaluza-Klein reduction, then remember that type 2a and type 2b theories have p-form fields with different, where p is even or odd in the respective theories. And so if I'm imagining compactifying these things down to lower dimensions, I can imagine, wrapping different dimensionalities of cycles depending on how many form legs I have available in my P form. And if I do this exercise and I can write some general P form field in my type 2a or type 2b string theory, in lower dimensions, I can write it as a Q form times a P minus Q form, the Q form in 4D and a P minus Q form on my Calabi-Yau, and I can enumerate the possibilities. And the possibilities will depend on the number of cycles available in the Calabi-Yau. And if you go through the exercise and get the form degrees right and everything, you'll find that the counting works out as I've just written it down in terms of topological numbers of these Calabi-Yaus, these Hodge numbers. And of course, quite strikingly, you see that there's a natural symmetry here, or a natural symmetry that one can propose. And mirror symmetry indeed will relate a type 2a compactification on some threefold X to a mirror compactification on some threefold X tilde, whose Hodge numbers are related. Well, they're exchanged. So vectors get mapped to vectors, hypers get mapped to hypers, and that means that the Hodge numbers of these manifolds get swapped. So these are topologically quite distinct manifolds. And I told you yesterday, last time in the example of the two torus, that mirror symmetry is T-duality. And before I move to the world sheet and spend the rest of my time there, let me just make a remark, which is a conjecture of Strominger, Yau, and Zaslow. The paper is called Mirror Symmetry is T-Duality. Mathematically, it's not rigorously proven, but widely believed to be true, that establishes this particular point of view on establishing this correspondence. And the Strominger-Yau-Zaslow conjecture says, view your Calabi-Yaus as a fibration of a three torus over some base manifold, something topological like a three sphere, for example. But the point is having these toroidal fibers. And the idea is if I start on one side, and this is my Calabi-Yau manifold X, say, then they tell you to perform fiber-wise T-duality on all three circles of the toroidal fiber. And so you'll obtain some mirror T3 to obtain X tilde. And it turns out that this swaps complex structure and complex moduli and Kähler moduli. But again, this is still a conjecture, but it's a nice picture to have in mind. And indeed, if you imagine starting with one torus and doing T-duality on all three of the radii, you're inverting the volume of the torus. And so maybe you can start to imagine that complex and Kähler moduli are getting exchanged under this map. And more generally, this kind of fits in with the picture of adiabatically constructing parts of the web of string dualities that we mentioned, I think, in the unrecorded part of the question and answers after my first lecture, where if you have some dual pairs of theories on some dual manifolds A and A tilde, like our T-dual circles or what have you, then you can imagine fibering these two dual manifolds over some base space and obtaining new dualities in lower dimensions. And again, this adiabatic principle of compactification works extremely well in string theory, sometimes better than it has any right to. I'm not going to say anything more about this geometry picture today, but yeah, go ahead, please.
Oh, I was just going to ask a question. Maybe it's naive, just about like how to get some intuition for this. I'm a little confused because in T-duality, the radius goes to 1 over the radius, but we're supposed to think of exchanging like H11 and H21, but like in my head, I've always thought of those things as like describing, different things you can change about the manifold. And I just don't see how something that seems like just changing the size of some cycle or something would correspond to changing like.
Sure. So maybe one way to motivate this, not in a full Calabi-Yau geometry, but in kind of a toy model, is to go back to the example that I mentioned at the end of last time with the two torus instead. So there, I just want you to think of the two torus as a circle fibered over another circle. And then what we did last time was just do T-duality, again, only on the fiber. And when we did T-duality only on the circle fiber, we exchanged the Kähler and complex structure moduli of the T2. The idea is that something similar can happen even if the fiber, the so-called special Lagrangian fiber, is actually a T3 over some other base.
I see.
Yeah, does that help?
Yeah, that makes sense. Thank you.
Sure. Okay, so now what I'd like to do is again move to the world sheet. And I want to talk about some general things like twisting and localization that are going to be ubiquitous tools all over the place in mathematical physics. And I'll mention kind of what the results are when you apply these things to the case of mirror symmetry. But mostly I just want to start introducing some very general concepts that should have broader utility for you wherever you are in life. Okay. And as I've been stressing, dualities don't have to follow from supersymmetry. Interesting mathematics does not require supersymmetry. Dualities don't require supersymmetry, but we can use supersymmetry in interesting ways to test putative dualities. And twisting and the formalism of twisting and related things like localization are going to be a great way to get computational control over a fairly rich set of observables on both sides of a putative dual theory. Or more generally, they can give you just good control to compute observables in a supersymmetric theory on its own, but in particular, it gives you a powerful way to test dualities when one side in particular might be strongly coupled or otherwise difficult to deal with in some respect. So I want to start by making general remarks about twisting before I think about mirror symmetry or any particular example. And I've been repeatedly saying the word twisting, and you might have heard instead the phrase topological twisting, which is something a little bit more specific, and I'll get to that later. But it's kind of a common misnomer in the literature to refer to things that are as topological twists, when more properly, they're just twists. They're not quite topological things, and I'll tell you what I mean as we go along. But roughly speaking, a twist is going to be some kind of operation that we can perform on a supersymmetric field theory, again, very roughly speaking, to restrict to a subspace of physical observables, restrict to, in particular, a supersymmetric or BPS subset of observables in the full physical theory. So everything I say today, again, it's going to be applied to SUSY field theories. So from the point of view of mirror symmetry, I'm going to be thinking about the supersymmetric string worldsheet as a 2D field theory on which I'll be applying this twist. There is an enrichment of the story that I'll tell you today on the worldsheet for mirror symmetry that promotes the field theoretic things I'm going to say today to a full string theory called topological string theory. And that's a much richer story, and it has deep connections with a lot of mathematics. But today I'm really going to be focusing, again, in the genus 0, if you like, genus 0 quantities in string theory. So twisted superstring theory or twisted superstring theory as a 2D SUSY field theory. And what I'm going to say about twisting applies generally to SUSY field theories. I'll make a remark that it's an active area of research to think about twisting supergravity theories directly, to extend this notion to something like a gravitational theory in space-time, not just on the worldsheet. That's something that various groups have worked on, notably, so let me just write Sugra, twisting, notably Costello and Lee. And I've applied this technology to think about dualities like the ADS-CFT correspondence from a twisted perspective, but I'm not going to talk about that at all today. I'm happy to talk about it with interested folks later on. But today we're purely in the world of supersymmetric field theories. And for the entirety of this lecture, I'm going to be in Euclidean signature. Okay, so at the beginning of last time, we reviewed BRST symmetry. And if you understand BRST symmetry, you already understand everything that I'm about to say. So remember that BRST symmetry is a proxy for gauge symmetry. And when I say a proxy, I mean a BRST symmetry is equivalent to gauge symmetry. If something is gauge invariant, it's BRST invariant, and vice versa. But BRST symmetry is a fermionic symmetry. So when we want to study symmetric quantities with respect to a fermionic, well, if we want to study symmetric quantities with respect to any symmetry, say any gauge symmetry or what have you, and we're interested in things that are symmetric under that symmetry, then we're going to be studying things that are in the kernel of the corresponding operator, things that are annihilated by that operator. In this case, in the BRST case, we were looking at things that were annihilated by the BRST charge, either states or operators. And these could be commutators or anti-commutators, depending on statistics of things. But in the case of a fermionic symmetry, not only are the states that you're interested in annihilated by those operators, but they're actually in the cohomology of those operators, because exact things with respect to a fermionic symmetry decouple. And remember, and we saw that last time, BRST exact things are trivial. They're zero in all correlation functions if you insert them. So when you have a fermionic symmetry, you're doing cohomology. Symmetric things, symmetric observables, form cohomology classes. And twisting is going to do the same thing. Instead of a nilpotent BRST charge, we're going to think about a nilpotent supercharge. And we're going to think about the cohomology with respect to a nilpotent supercharge. And we can choose any one in whatever superalgebra we have that we like, and we can go forward. And a lot of the same arguments, such as the vanishing of exact quantities, go through in exactly the same way. Okay, so twisting means choosing a nilpotent supercharge and working in its cohomology. Nothing more than that. So physical states in a twisted theory are Q closed. And I'm going to focus on operators for all of today's lecture. Of course, there are correspondences between states and operators, particularly in superconformal field theories, which we're going to be especially interested in, but let's be operatorial today. And again, we're further going to assume that the supersymmetry isn't spontaneously broken, so Q annihilates the vacuum. And then these physical operators are naturally identified up to the addition of Q exact terms. Remember, by the same argument we saw last time, if we're studying correlation functions of Q closed operators and we insert some Q exact thing, then we can expand this out, anti-commute all the Q's past these Q closed objects. It'll hit the vacuum, and by assumption, it will die. Okay. So we have a fermionic symmetry. And that means, again, we're doing cohomology. Good. So again, in the BRST formalism, what this kind of amounted to restrict to gauge to naturally quantized gauge invariant states involved us introducing this BRST charge, which could be built in a certain way out of the various ghost fields that I wrote down. And in particular, there was an additional U1 symmetry at play there, a ghost number symmetry. And if you like, you can grade all of the states. You can label them by their ghost number. And the BRST operator is going to increase the ghost number as it acts, because it's made out of ghosts, and it has, in particular, a positive ghost number. So this is just like when you're studying cohomology of ordinary differential forms. You have some differential, like the de Rham differential, and there's some complex, like the complex of differential forms on a manifold, the space of all differential forms on a manifold. This is graded by form degree. We can think of P forms, 1 forms, 2 forms, and so on. So it's graded by form degree. And there's a differential that maps between the graded subspaces in this complex. Takes P forms to P plus 1 forms. And so on. And then the cohomology of this complex in the ordinary case localizes you on harmonic forms, as it turns out. Forms that are annihilated by the Laplacian operator. One could consider the isomorphic cohomology in terms of the del dagger operator, and the result is the same. So BRST cohomology works the same way. The grading is now replaced by the ghost number symmetry. Mathematicians will call this the cohomological grading of the BRST complex. So you'll see that terminology a lot. So in math, ghost number is called the cohomological grading or the cohomological degree. But the BRST charge acts as a differential on this complex of states, and cohomology, the cohomology becomes the gauge invariant, the BRST invariant of variables. And again, in twisting, things work very similarly. We have some supercharge that's going to act as a differential on our Hilbert space, where we view our Hilbert space as a complex that's graded by, whatever conserved quantities we have in the game. And we're at least, at the very least, we're always going to have a Z2 grading on the Hilbert space. We can stratify the Hilbert space by fermion parity. Can split into bosonic plus fermionic pieces, and the supercharge is going to map bosons to fermions and vice versa. But more generally, we can have superalgebras with extended supersymmetry. We might have U1R symmetries, for example, and that might give extra gradings on this complex. Can get extra Z gradings, and so on and so forth. But a Z2 grading is also enough to define an index. You may have seen the Witten index, which uses the Z2 grading to compute this enriched version of the partition function called the supersymmetric index. And kind of the more gradings you have on your complex in math speak, the more interesting and different kind of invariants you can compute that employ all of these gradings, which are just acting on our Hilbert space and extracting eigenvalues of the corresponding symmetry from our operators, so supersymmetric indices. So in the simplest case, the Euler character of the complex in the de Rham case can produce the Euler character of the manifold, the topological invariant. Which is like the simplest supersymmetric index. So most of the time, in the most general contexts, in a twist, we're working not just with a supersymmetric theory, but also with a gauge theory or string theory. So usually we have both gauge symmetries and supersymmetries in the game. And what that really means, so what twisting really it does, means that if you start with a BRST differential and you're covariantly quantizing using the BRST formalism, twisting is an instruction to take your BRST differential and add to it the twisting supercharge that you want to twist with respect to. So it's like, so instead one is taking cohomology with respect to this total differential. Now, very, very heuristically, you might think, okay, so this the physical states with respect to this twisted differential will be things that are gauge invariant and also Q closed or Q invariant or BPS with respect to Q. This is all different words for the same thing. That's kind of a useful first order approximation. It's not actually true in practice, and this is a subtlety that we tend to gloss over in the literature. To properly compute the cohomology of this additive thing, you need to use techniques like spectral sequences, which I'm not going to cover at all in this course. But I just want to mention them to let you know that when twisting, properly speaking, you need to be a little bit careful about what you think the result of the cohomology problem is. It's not necessarily going to be the intersection of gauge invariant things with Q-closed things. Generally, it can be something different, but I'm not going to go into that because it's a bit too much detail work.
Is there a simple example to look at where that happens, where that comes up?
Yes, but I would need to dig around a little bit. I can give, if you remind me on Slack,
Will do.
I'll give references and stuff. Yeah, and this is also true if you twist supersymmetrically, say to some interesting protected sector, and then you're like, okay, this sector is great, but it's a little too complicated. Let me add another supercharge and further twist and go to something even simpler. You have to do a spectral sequence if you really want to do things properly. And sometimes that's not just being fussy, that you actually need it to get the right answer. Yes, I heard another question.
Yeah, how do you get an intersection? Seems like you could get things that are neither gauge invariant nor supersymmetry invariant that together manage to give you something that's zero.
Yeah, So this kind of employs the technology of spectral sequences a little bit. Typically, you start by pretending you just have one differential and you compute the cohomology with respect to that. And then the spectral sequence is a way of improving taking that 0th order approximation and then correcting it. So the 0th order approximation is going to start with, say, a BRST closed thing. But I don't want to kind of get into the details of that. It often turns out that the spectral sequence will collapse into something like an intersection, but it's not always going to happen.
Okay.
Okay. So that's twisting. That's all twisting is. You're just doing more cohomology. But there's something that historically often comes up that's a little bit of a richer and more useful story. And this is really the province of topological twisting. And I'll mention a generalization that's useful a little bit later on. So what I said is perfectly fine if you want to study your supersymmetric theory on fairly simple backgrounds. You may want to study the theory on more exotic, compact backgrounds. For example, in 2 dimensions, when I twist a world sheet, I might want to make sure that I still have a well-defined theory on various Riemann surfaces of all genera. And this is where topological twisting comes in. So remember, I'm in Euclidean signature for the duration of this talk. My original physical theory before twisting is going to have my Euclidean Lorentzian group spin D in D-dimensional flat space, acting as rotations on my Euclidean plane. And Q, of course, is my twisting supercharge is a space-time spinner. It's not invariant under the entirety of spin D. And as a result, if I just don't do anything else and take the cohomology with respect to spin D in general, I'm not going to preserve the full Lorentz symmetry of the underlying physical space. So if you have some symmetry in your physical theory and you want to preserve it in cohomology, you have to do another step. And the cost of this is that you restrict ultimately to kind of a less rich, a little bit less refined set of observables, but you preserve more symmetry. So there's kind of a trade-off when you take this extra step. It depends on the physical application that you might be interested in doing. So what's the strategy? What we want to do is instead of having Q be a spinner, well, as it is under the usual spin group, what we do is modify the action of the Lorentz group such that the twisting supercharge that we want to work with becomes a scalar with respect to this new twisted Lorentz group. So formally speaking, I have some other Lorentz action spin D prime that I want to impose, or that I want to have. And so formally speaking, I'm choosing a homomorphism phi from spin D into my R symmetry group. So I'm assuming that my superalgebra is extended. It has some non-trivial R symmetry group, GR. So phi is called the twisting morphism. It twists the Lorentz group by an additional R symmetry action, twisting morphism. We'll see an example in the case of mirror symmetry. But what it's doing is replacing the spin D group by another group, spin D prime, that becomes the new Lorentz group. And on flat space, spin D prime acts the same way as spin D on the geometry on space-time itself, but we are modifying the action of this new Lorentz, we're modifying the action of the Lorentz group on the fields in the theory. We're modifying their Lorentz spin by their R symmetry charge in some way that is dictated by this choice of map that I'm making. More generally, if I could choose, some other group G and consider other kinds of twisting morphisms into this space, if I wanted to preserve, say, some subgroup symmetry G in my twisted theory. But typically one is interested in a topological twist where you modify the action of the full Lorentz group and get a Lorentz invariant thing. So choose such that Q is spin 0 with respect to spin D prime. And again, in mirror symmetry, we're going to go through examples of all of these things.
Are you requiring that phi be injective?
Yes.
Maybe at least on the level of Lie algebra.
Yeah.
Great, thanks.
I believe I am. And of course, I should say all of these things have been classified quite rigorously, and I can certainly point to references that exhaust the list of possible twisting morphisms given your favorite, given the complete list of superalgebras in various dimensions. So this work has all been done carefully. Okay, so doing this topological twist, doing this extra step of applying the twisting morphism has some nice properties. One of the things that happens in most cases is that the modified stress energy tensor becomes Q exact. So let me say in the twisted theory. So not only is the stress energy tensor symmetric with respect to my supercharge Q, it's symmetric in a trivial way. It's exact. It has no influence in cohomology. And consequently, if I take, if I want to consider various conserved charges that come from integrating T0 beta over some slice to obtain things like momentum charges, that means those are going to be trivial as well. So generically, it turns out, only the integrated translations are guaranteed to be Q exact for the most generic kind of twist. So translations, momentum generators. So let me just say momentum corresponding to translations in my spatial directions are always Q exact after doing this topological twist. But in also the vast majority of the cases, the slightly stronger statement involving these local densities that all the components of the stress energy tensor are also Q exact as well. And that has some really nice properties. So since translations are Q exact, they are trivial in cohomology, which means correlation functions of Q closed observables cannot depend on the positions of the operators. So, explicitly, if I have some translation operator and I want to know how it acts on my correlation function of Q closed operators, and let's say the momentum or translation operator is Q of, I don't know, let's call it Q of eta. Then as always, I can do the same kind of manipulation that I already did in the BRST case. Pull the Q kind of outside of everything, and it is 0. So correlation functions are independent of position of these Q closed operators, of operators in the twisted theory, are position independent. Because Q exact quantities are symmetries of the twisted theory, they vanish in these correlation functions. So what does that mean? That means if I have some Q closed operators and I want to study them and bring them together, the operator product that I would have that's normally some position dependent thing, in particular, it will probably have singularities as I bring the operators closer and closer together, actually is not allowed to have these coincident singularities as the operators approach each other, because those would depend on some inverse power of the positions or the distance between the two operators. So in particular, so these operators in the twisted theory will form an honest algebra. If I collide them, I don't obtain singularities. And I'll talk about that algebra in the mirror symmetry case, in the full topologically twisted theory. So I can collide them and I won't get singularities. I'll get actually the structure of what mathematicians call a ring structure. So as I said, the choice of this twisting morphism is optional, or I can consider generalizations of it where I don't necessarily try to preserve the full spin D symmetry. And there's a more general class of twists, it turns out, in general dimensions on flat space. on flat space in particular, although not only on flat space, where one gets more general kinds of twists that are often called holomorphic or mixed holomorphic topological twists. So these have been studied a huge amount recently in the context of various supersymmetric field theories and also in the context of topological string theories. And I've been thinking about these twists also in the context of ADS CFT, both on the boundary and in the bulk. And with a holomorphic twist, without choosing these twisting morphisms, what you find is that rather than having all of the translation generators being Q exact, in the absence of the twisting morphism, just looking at the cohomology of Q on its own, you find that in general, some of the translation generators might be Q exact, like in mixed holomorphic topological twists. So it might be topological in some directions, but in other directions, in particular, if we have an even number of dimensions, only the anti-holomorphic derivatives may be Q exact. So I might have a position independent algebra structure of operators in one of the directions if I have some topological dependence, but in other directions, the operators, when they collide with one another, for example, in correlation functions, they may be allowed not to have any interesting Z bar dependence, but still have some interesting Z dependence in their collision product. And so, for example, you can see this sort of on the copy of the complex plane. If I holomorphically twisted a conformal field theory, I would obtain what's called a chiral algebra. The Z bar dependence in the OPE of my conformal field theory would drop out, and instead, I retain only the holomorphic dependence. On the position. And that's the right structure to get what's called a chiral algebra, or basically the holomorphic half of a conformal field theory. So you can get richer algebraic structures than just these ring structures that appear in the topological case. You can get things like vertex or chiral algebras more generally. And in higher dimensional theories with mixed holomorphic and topological directions, you can get interesting, more exotic structures that kind of mix these topological products that are position independent with holomorphic products that are dependent only on the holomorphic coordinates. And I won't say too much more about that in these lectures, but I'm happy to provide a bunch of references and talk more about it on Slack. I want you to be aware that this generalization exists. And in fact, you can define, for even dimensional theories, you can define holomorphic twists as well on Calabi-Yau manifolds. So that turns out to be a good thing to do. But let's go back to the arena of topological twisting for the moment, when I'm really just killing all of the position dependence of my operators. All of the translations are trivial in cohomology. Indeed, I even have a Q-trivial stress tensor. And let me just remark that one of the reasons you might want to really do this full topological twist is because you can define your theory in general on curved manifolds in a supersymmetry preserving way, in a way that preserves at least the supersymmetry given by the twisting supercharge. So in general, I might be interested in some supersymmetry transformation that's like epsilon times my supercharge Q that I'm interested in. So epsilon is some spinor parameter, as you guys have seen before. And in the twisted theory, as I've told you, I've arranged for the spin of Q with respect to my new spin D prime Lorentz algebra to be of spin 0. And even though, okay, this parameter is still anti-commuting, but now in the twisted theory, it's spin 0. And so this covariantly constant spinor condition that showed up last time can actually be satisfied in the twisted theory. I've changed the spin of epsilon so that the constant parameter, it's a spin 0 thing, and constant things can be annihilated by covariant derivatives. You can parallel transport them all they want, they're trivial. So this is a way to preserve some SUSY, might preserve Q SUSY on general curved manifolds. And of course, I think it was a question that came up last time of, okay, more general things in string theory are possible. We can turn on Ramond-Ramond fluxes and also modify this covariant derivative, you know, instead of thinking about the covariant derivative with respect to the Levi-Civita connection, you can also turn on things like fluxes, and that will modify the killing spinor equations. And that is the sort of context in which you get Freund-Rubin compactifications like ADS5 cross S5. So I think that was a question last time. And certainly you can do that. You can turn on fluxes for all sorts of things in sources and string theory and modify the killing spinor equations that way and try to preserve supersymmetry on various interesting curved manifolds. And here we're doing something a bit different. We're changing the spin of this guy, this spinor parameter. And we can preserve Q supersymmetry in particular on two-dimensional Riemann surfaces of arbitrary genus in the context of the mirror theories. Okay. As always, I'm running a bit behind, but are there any questions on that? Okay. One could also imagine another modification to this story, which I won't really say much about for the rest of the lectures, but you could imagine wanting to study a supercharge that doesn't square to zero, but rather say maybe you've taken some interesting linear combination of the supercharges in your original superalgebra, and you have something that squares to some bosonic generator, where J is just some bosonic generator that could be some combination of global symmetries, gauge symmetries, diffeomorphism symmetries, whatever. And then this modifies the notion of cohomology to something called equivariant cohomology, where now you study things that are J invariant. So if J is acting on a physical state and annihilating it, then on that space of states, so for states where JO is 0, you effectively have another cohomology problem. And you can study that too. And mathematically, this goes by the name equivariant cohomology. And it also comes up very frequently in physical contexts, like when you're placing theories in the omega background, or trying to study supersymmetric field theories on various interesting supersymmetric theories in various interesting supergravity backgrounds or non-trivial geometries. So this modification comes up too. Now, before I move to illustrating things in the example of mirror symmetry, I wanted to say some general words about localization because it's kind of the prototype technique to compute quantities in these twisted theories. Not only in these twisted theories, it's a more general set of techniques in which to work and compute various various BPS observables in a variety of theories. But in particular, in the context of twisted theories, you can use localization to compute things like supersymmetric indices and correlation functions of operators in my twisted theories. So I will say a lot more about this in the notes. And I don't have too much time today, so I don't want to give a really long exposition on it. In fact, I'm trying to think of how much I might want to skip in real time. Roughly speaking, localization is a way to compute path integrals exactly for certain quantities. I can't get all of the physical quantities that I want to compute, of course, in this way, but for certain Q closed quantities, it's a way to obtain exact results. And it's based on this idea of equivariant cohomology that I've mentioned before. So I want to do this rather briefly, but let me try to sketch the idea quickly if I can. So in general, when we're doing some kind of integral over some manifold M, we know how to do these integrals in the language of differential forms. And we know that integration cares about cohomology classes. If I'm integrating some form like d beta on a closed manifold M, I'm going to get 0. So, so ordinary integration is sensitive to de Rham cohomology. Ordinary integration is about de Rham cohomology. But let's say M has some symmetry group G that acts on it, and I want to consider G invariants. I want to consider the G invariant integrals over M. So roughly speaking, I want to integrate over something like M mod G. If this is a smooth space, if there's no fixed points, i.e. The group acts freely, G acts freely, then I can just integrate in the same way that I always do using my usual notion of differential forms and Drame cohomology, and everything works the same way. But there are some spaces that might have fixed points. So G can have fixed points, and that leads in general to singular spaces over which to integrate. And one has to modify the notion of cohomology such that when one is working in the smooth case, your generalization will reproduce Drame cohomology again, but extends that notion such that I can actually integrate things in this more general situation. And that's what equivariant cohomology does. So it modifies the de Rham differential to some kind of equivariant differential. So let me say G is some abelian group and V is an associated vector field. There's a way to modify the de Rham differential into some equivariant differential. And I give formulas in the notes and many more details. And one can instead consider equivariant cohomology. So namely, one can consider dV closed forms mod dV exact forms, which are in particular forms annihilated by the action of this differential. Okay, and this is the basic idea of supersymmetric localization as well. So the result is that integration depends on the equivariant cohomology class of the forms. So you're studying forms that are symmetric with respect to this G on the equivariant cohomology of the forms. And whenever something depends only on cohomology, a way to get convenient answers is to take whatever thing you're integrating, it's defines some cohomology class, and you deform it. You can deform it by as many exact terms as you like. And you can do that deformation in such a way that you're integrating the most convenient possible form that you could integrate. By the cohomological properties of integration, this is still going to give you the same answer as the original integral you were trying to compute. And it turns out that when you do this, if you make a judicious choice of representative, you can show that the integral will localizes to v fixed points. So the integral can be computed exactly. V symmetric contributions only. In the context of supersymmetric field theories, localization is equivariant cohomology for Q, including cases where Q squared equals J, and integrals can be computed exactly, and they localize to Q invariant field configurations. And what one does is to take an expectation value. So let's say I'm interested in some expectation value of a Q closed operator O. And I assume that the path integral measure is invariant under Q as well. And of course, my action is Q invariant. O is Q closed because I'm studying Q invariant things. I can deform my action by some Q exact term. Nothing depends on that. And very roughly speaking, I can make any choice of V that I like such that the problem is as simple as possible. If I'm in this equivariant case, then V has to also be J invariant. That's the equivariant part of equivariant cohomology. You have to consider J invariant things only, but I still have a choice of V. And this is the same kind of thing we did when we were doing BRST quantization as well. When I was doing BRST quantization and I wanted to compute gauge invariant things, I added a term that was dB of something. That was my gauge fixing in Faddeev-Popov term. It could be written in a BRST exact thing as well, and that produced a gauge fixing of the path integral. Here, localization is doing something similar, and it will enable me to compute the action, or it will enable me to compute this quantity, and this quantity will localize on Q invariant field configurations. Just like in BRST, I spat out gauge invariant things. And in particular, one can show that this thing, so I put some parameter t in front of my Q exact term, and I can pretty easily show that dt of this thing is 0. So if I take dt, I bring down a Q exact piece, and if I make various appropriate assumptions about the behavior of things at infinity that I'm going to suppress but go over in detail in the notes, well, I know that Q exact things are trivial. That means d dt, the dependence on this parameter, is trivial, and that means the t equals 0 answer, the original thing that I wanted to compute, is the same as the t goes to infinity answer. And at t goes to infinity, I can do some purely semi-classical computation. I can do actually a one loop exact computation in terms of this deformed action. And maybe that's all I want to say about that. Again, I'm happy to say more after, and I give many more details in the notes, but the basic idea is that for localization, I'm going to need to consider Q invariant field configuration. And that's all I'm going to need, I think, in the rest of the stuff that I want to say about mirror symmetry. And that's where I want to turn to next, just illustrating all of these things much more concretely in the example of mirror symmetry from the world sheet. Okay. Questions before I make everything hopefully more clear in the context of this example?
Yeah, could you just say what the minimum data required for cohomology is? Is it a manifold with a free group action? That's all?
Yeah, good. At the moment, all I need is a manifold with a group action. It does not have to be a free group action. An equivariant cohomology is exactly designed to deal with the case when it's not. And it reduces to de Rham cohomology when it is. Yeah. Yeah, maybe that's all I'll say for now. Okay. So I cheated a little bit in that I put aspects of supersymmetry as part of your background or kind of homework reading to prepare you for the lecture. I'm not going to do too much explicitly, but I am going to use a little bit of superfield formalism to illustrate things and write things more concretely. So again, mirror symmetry is going to be an isomorphism between two physical theories. I have a duality that exchanges 2A on some Calabi-Yau manifold with 2B on its mirror Calabi-Yau manifold, and this is a physical equivalence, but I'm going to do twisting in order to help compute and check aspects of this duality. I'm simplifying my physical theory by boiling down each side of the duality into two twisted theories where I can compute things via localization and compare things quite directly. And in particular, it turns out that if one is studying, say, well, it turns out that the right context for mirror symmetry is going to be two-dimensional 2, 2 supersymmetry. And for theories that have geometric interpretations like sigma models with maps some target manifold, this is associated with Kähler manifolds, of which Calabi-Yau manifolds are a special case, but actually mirror symmetry is something more general than just Calabi-Yau manifolds. I'm not going to prove this, that Kähler manifolds means 2, 2, but it turns out to be true. So with 2, 2 supersymmetry, I have two supercharges that are labeled by their spin or chirality under the 2D Lorentz group. And I also have their Hermitian conjugates. So any representation of the supersymmetry algebra can be packaged into some supermultiplet where I introduce now Grassmann coordinates associated to each of the supercharges I have. And I can Taylor expand this thing in terms of the Grassmann coordinates, something like this. And in total, I'll have a general multiplet will have 16 components in this kind of expansion. But supermultiplets are a convenient way to package, to make supersymmetry manifest and repackage things in a convenient way. And in the 2,2 case, there are two important U1 symmetries that will serve as R symmetries. They can act on superfields in these theories. They're called the vector and axial symmetries. So in terms of the supermultiplets, the vector symmetry will act on a superfield of charge QV like so. So it doesn't touch the bosonic coordinates, but it does rotate the Grassmann coordinates. And on the axial, an axial symmetry will act on a charge QA superfield like so. So even if I'm studying superfields that are overall of charge 0, that means their lowest component will be of charge 0. But because I'm going to have rotations on these Grassmann coordinates, the other components will in general have non-zero charge. And let me display explicitly how it acts on this, how these things act on the supercharges as well. So vector acts on the supercharges like this. So it is an R symmetry. There is a non-trivial action on the supercharges. E to the minus plus I alpha. Okay. And these U1 symmetries may or may not be preserved in any given 2,2 theory that we study. They are optional. We will be focused on most of the Calabi-Yau case, where the U1 symmetries are preserved, and indeed the Calabi-Yau sigma models are not merely 2,2 supersymmetric, they're actually 2,2 superconformal, and the U1 symmetries become part of the 2,2 superconformal algebra. But again, for the moment, I'm being more general. I'm considering general 2D 2,2 quantum field theories. And let me write down the n equals 2,2 algebra in terms also of the Hamiltonian, the momentum, and the angular momentum, which in 2 dimensions you can also write down explicitly in terms of familiar things. So hopefully I'm not getting factors too terribly wrong. And as always, when I write down an algebra, anything I don't explicitly write down has 0 commutator or anti-commutator. So of course, so these supercharges are all nilpotent. Almost done. And again, notice the vector and axial symmetries are acting on the supercharges in the prescribed way. So all of the non-listed anti-commutators are vanishing. You can relax some of the vanishing anti-commutators to write down what are called central terms in the algebra. We will primarily not consider this generalization today, but I again want to mention them to you as a generality that can happen. You can consider these things, and these central charges govern the mass of BPS solitons in more general 2D 2,2 supersymmetric quantum field theories, and they've been studied in that context in interesting ways, but they have to commute with all of the generators of the algebra, and in particular, if we're demanding that our theory preserves the vector and axial symmetry, these things have to be 0. And for the Calabi-Yau case, they're going to be 0, so we're going to ignore them. But now I don't have to even write down any specific theories or specific Lagrangians to tell you what mirror symmetry is. Mirror symmetry is a Z2 automorphism of this 2,2 algebra. Mirror automorphism. Notice that all of these things I've written down, provided I didn't mess up any minus signs or things like that, are completely symmetric if I make the following exchanges. If I exchange these supercharges, exchange the vector and axial symmetry, and in a more general theory, I can also swap these central charges. So 2,2 theories are mirror to one another if there's an isomorphism of their Hilbert spaces that transforms the generators of the superalgebra by this corresponding mirror symmetry involution. So in particular, it is not something that only works for Calabi-Yaus, although it was discovered in that context. It is more general. And when you have a theory that preserves vector and axial U1s like Calabi-Yaus, it will exchange those two symmetries. But more generally, for example, you can have a mirror theory where one pair has a broken vector symmetry and an unbroken axial symmetry, and its mirror symmetry will have a broken axial symmetry and an unbroken vector symmetry. So again, these more general things are possible. Good. So I need a little bit more technology. I want to employ some particularly simple representations of the n equals 2, 2 superalgebra to study Calabi-Yau theories. So let me introduce these standard derivatives on superspace. Which anti-commute with the supercharges. So they act on my superspace in this way. They satisfy very similar commutators to the supercharges with things like the Hamiltonian and the momentum. And in fact, the supercharges can be written in a superspace language by just replacing, by exchanging the kind of relative minus signs here. So make this one, make the top one a plus and the bottom one a minus. Okay, but these things commute with the supercharges. And in terms of these things, I can define a chiral multiplet to be a superfield that satisfies d bar plus equals 0. And its complex conjugate antichiral multiplet will satisfy the conjugate condition. And you can also define things called twisted chiral multiplets, which satisfy very similar conditions. But today I'll focus only on theories with just a bunch of chiral multiplets. That's the most interesting ones for me today. And they have relatively simple expansions into coordinates. So I'm going to be a little bit sloppy here in view of time, but in particular, the bottom component is going to be some scalar field. There's going to be two fermions, which multiply the Grassmann coordinates, and there's also an auxiliary field here, F, which can always be replaced by its equation of motion. So if I'm looking at a theory with multiple chiral multiplets, the degrees of freedom I'm going to care about are scalars and fermions, and also the complex conjugates. So there's also phi bar where I complex conjugate everything. And you can write down supersymmetric Lagrangians in terms of these multiple chiral multiplets. Of course, it's not the most general 2, 2 theory, but in particular, you can write terms like a Kähler potential, which is written in terms of an integral over all 4 Grassmann coordinates over all of superspace. And you can also, so these are often called D terms, and you can also write down F terms, which are coordinates, which are integrals only over half of superspace. And these are some holomorphic functions of the chiral multiplets only, whereas the Kähler potential will depend on the chirals and the antichirals. And similarly, there's a twisted F term that I won't write down in view of time, but I mean, you basically integrate over the other two obvious coordinates. And you can ask when these two terms, if I'm trying to write down some supersymmetric Lagrangian, will preserve the U1R symmetries. The terms have to preserve the symmetries independently, the U1, since they don't mix under vector or axial rotations. And in the case of a Kähler potential, the measure is invariant under both the vector and the axial symmetries. So as long as you can make a charge assignment of the chiral fields such that this Kähler potential has total charge 0, then the D term will preserve both of the symmetries. And also something like this also is often chosen and does the job. On the other hand, the F term has this measure, which transforms with charge -2 under U1 vector, but 0 under U1 axial. So the superpotential, if you assign all of the chirals to have charge 0 under the U1 axial, then the F term preserves the axial symmetry, at least classically. But if you want to preserve the vector symmetry, then the superpotential has to satisfy a condition called quasi-homogeneity. So it has to transform with an overall charge 2, and you need to cook up the charges in form of the superpotential so that it does this. So that's classically how you can preserve the symmetries in any given 2,2 Lagrangian that you'd write down, at least one that is only a function of chiral multiplets and no other interesting multiplets. But you can have anomalies at the quantum level that can break these R symmetries. And I don't have time to go through the analysis, but it turns out that you can relate this in the case where you're studying a sigma model with some geometric target to a geometric condition that we've seen before, namely vanishing of the first Chern class. So Calabi-Yau sigma models, in particular, will preserve the axial symmetry quantum mechanically. A general Kähler manifold with non-zero Chern class will break the axial symmetry. And a Calabi-Yau is good for both. Okay, so when one is studying mirror symmetry, we can imagine a 2D2,2 theory that's given by some sigma model whose target is a Calabi-Yau. And so I'm imagining that I have some, in general, complicated theory with a bunch of chiral multiplets, and I have some, at least some perhaps very complicated D term that I'm studying. And what I want to do is to consider two twists of a 2D2,2 theory, in particular sigma models with Calabi-Yau target. And I will make two choices of twisting supercharge. And notice from the form of the mirror automorphism that they will be exchanged under mirror symmetry. So the A twist of one theory is going to be equivalent to the B twist of the mirror theory. And those are the kinds of things you want that we will check. And we can consider either the QA cohomology or the QB cohomology, depending on which twist we want to take. And I can focus on the cohomology of operators. So, and remember, and these will form a ring of operators. I will shortly do an honest topological twist, but right now I'm just considering cohomology. Prior to any choice of twisting morphism, I will make a choice of twisting morphism when I study these theories, however. An operator is called chiral if it satisfies the condition that it's annihilated by QB, and twisted chiral if it's annihilated by QA. In particular, because the lowest components of the chiral and twisted chiral multiplets turn out to be operators in the cohomology of this type, but it's kind of a misleading name because you can consider more general operators. But anyway, this is just kind of the name of operators that are closed with respect to the two supercharges that we're working with. And these operators indeed satisfy the property that worldsheet translations are exact. They're Q exact for either choice of Q. For example, del plus O, translation in, say, the plus direction. you can just do some super algebra manipulations to verify that the translation is indeed Q exact. In fact, this works for both twists and both directions. So given two chiral operators or two twisted chiral operators, their product will also be a chiral operator or respectively a twisted chiral operator. So taking Q cohomology is going to produce what's called a chiral ring for QB or a twisted chiral ring for QA. Again, I don't really like the names, but that means the operators in this theory have an operator product, again, with no position dependence because we've killed position dependence up to some Q exact stuff. And these are the structure constants of the chiral or the twisted chiral ring. They're fully determined by 3-point functions on the sphere. Again, I'm being genus 0 this entire way, as well as 2-point functions. So all I need really is 2-point functions and 3-point functions to learn everything I really want to learn about either the chiral or the twisted chiral ring. Kind of similar to what you've seen in conformal field theories, but here it's 2D topological theories, so life is even simpler. And this operator product is associative, and it contains the cohomology class of the identity operator, so it satisfies all the axioms of a ring. I went a little slower today than I want to, so I only have a few minutes. So let me conclude. I'm going to skip the Q cohomology of states entirely. Of course, states and operators are related. Maybe I'll mention it briefly next time just to say the words, but it turns out that either for QA or QB, if you consider the Q cohomology of states, you localize to supersymmetric ground states. The cohomology computes the supersymmetric ground states of the corresponding theory. And computing the Euler characteristic of the resulting complex gives the Euler characteristic of the manifold in the case when you have a geometric interpretation for theory. And yeah, it's not hard to do the analysis in more detail, and I'm happy to do it offline or next time if there's interest, but I'm going to skip it for now and focus on operators. And let me just write down the twisting morphism. So again, I'm in Euclidean signature. I can write all of the position dependence in complex coordinates. And so instead of having an SO11 Lorentz group, I'm being Euclidean. And I have an SO2 Lorentz group, which is just U1. And I'll denote it by U1L for U1 Lorentz with generator M sub L, just to distinguish it from the R symmetries, the vector and axial R symmetries that I might have. And so for the A twist, I make the choice of twisting morphism that the generator of my U1 prime is the sum of the original plus the vector symmetry. And in the B twist, I modify it by adding the generator of the axial symmetry. So if you're studying a theory that breaks axial symmetry, like a sigma model with target some Kähler but non-Calabi-Yau manifold, you can only do the A twist. And this is, of course, going to change the spins of all my operators because I'm taking their original Lorentz spins and I'm adding to them whatever their corresponding U1R symmetry charges were and declaring that those are the new spins under the twisted theory. And you can check that QA or QB under these respective twists become scalars. And furthermore, you can also check that after you do this twisting morphism, you can take the original stress energy tensor of the theory, it will modify it by shifting it by currents of the appropriate R symmetry, again, either the vector or the axial, depending on if you're doing the A or B twist. And in either case, you do get a Q exact stress energy tensor. So all of the metric dependence of the theory is cohomologically trivial, and the A and B twisted models are cohomological field theories. Topological. They're cohomological field theories, but in particular, they are topological theories on our 2D worldsheet. And I am out of time, so I will end here. And next time I will briefly tell you more about the local operators in the A and B twists of the 2D2, 2 theories that come from sigma models whose targets are Calabi-Yau manifolds, and tell you the geometric interpretation of those local operators, and then move on from there to other applications and other sort of more fun and modern stuff if I get to it. So yeah, that's it for today.
Wonderful, thank you. Excellent. All right, questions for Natalie? Everything was so very clear.
Everyone's
yeah,
tired,
I have a question.
Shoot.
You said that for these, I wasn't sure if I understood you. You said that for these cases, the twisted theory is the same as the supersymmetric ground states. But is that true in general, that the TQFT you obtain by a topological twist is the same as like the TQFT of a gapped theory that you flow to the IR?
Good. So let's be a little bit careful. For these two theories, for either the A and the B twist, the Q cohomology of states, the states in my theory give the supersymmetric ground states. The operators give these richer things, the chiral and twisted chiral ring. So to say that I've localized onto the supersymmetric ground states is a little bit, I have to be careful that I'm talking about states as opposed to operators. Of course, in CFTs, there's a correspondence. But sorry, what was the rest of your question?
The question was just that there's two ways I can see getting a topological quantum field theory from a supersymmetric theory. One is by twisting, and the other would be, if it's gapped, by flowing to the infrared. Is there a general relation between those two?
There's certainly a relation, but I don't want to say that a twisting will automatically give you just only the ground states. For example, in the holomorphic twist, you don't just localize on the ground states, you get a richer set of states in Q cohomology. Yeah, it so happens that when you take, so since you asked, maybe I can say a couple words about it. If I can do it quickly, maybe. Well, yeah, maybe I don't want to take up too much time with a huge answer, but the basic idea is that if you're considering the Hilbert space of a theory and you're grading it by the energy eigenvalues, and we're also grading it in the super case by the fermion parity bosons or fermions. And you can look at how the supercharge that you're interested in maps you between the bosonic and fermionic subspace, but it preserves the energy eigenvalue because Q and its Hermitian conjugate will anti-commute to the Hamiltonian. And if you just write down the complex with this differential and you try to compute the cohomology, you find that in this case at non-zero energies, when the energy eigenvalue is non-zero, the sequence is completely exact. Any Q closed thing is actually a Q exact thing, and it's trivial. And it's only the zero energy states, because I sort of don't have a non-trivial co-boundary operator that's mapping into it, are the Q closed things actually non-trivial. Basically, there's nothing Q exact that could map into them and make them trivial when I do cohomology. And so that's a feature that's a bit special, kind of to these twists. They kind of, when you take the Q cohomology of states for these A and B models, for example, the cohomology brings you down a lot. That's not going to happen all the time. In particular, you can think of a half twist. Actually, am I saying something? Yeah. Yeah, good. In particular, you can think of a half twist of these 2D theories where I only twist by, so instead of doing a full QA twist, I can just try to twist by one of them, Q bar plus, and things will be richer and more interesting there. I'm not going to get topological dependence. Does that answer your question?
Yeah, I think that
If I
answers my
understood
question.
the question.
Yeah, I'll think about it a little bit more. Thanks.
Other questions? Okay, maybe we'll end the recorded part then. Thank you.